Hi, this tutorial goes with the Honors Chemistry Unit 8 notes. This is an introduction to moles. So you've been looking a little at moles the last few days. Mole is a unit in chemistry that is used to make large numbers more manageable. For an example, if you had 100 milliliters of water, that's not really very much, maybe a couple of gulps. There's 3.34 times 10 to the 24th molecules of water in that 100 milliliters. Remember that molecules, atoms, ions, and formula units are very, very tiny, less than microscopic. So to count them means that you're counting very large quantities. That 3.34 times 10 to the 24th and a couple gulps of water is this long number here with all the zeros. So really, too many to count. But what scientists did was they made a unit called the mole, because 100 milliliters of water is only 5.6 moles of water. That's a lot easier to picture. 1,000 milliliters of water, or a liter, is 55.6 moles of water. Again, we can compare moles a lot easier than we can compare molecules. Look at these comparisons down here. 100 versus 1,000, 5.6 versus 55.6. Those are numbers that we can comprehend in our heads. But if we were looking at molecules, this number versus this number, those are just way too big of numbers for us to really understand what's going on there. That's why it's really a great unit to have the mole in chemistry, because it helps us to be able to quantize things where we can actually understand what those numbers mean. It should be becoming obvious why we count in moles. It's kind of like counting donuts by the dozen or fireworks by the gross. You buy a dozen of donuts because it makes sense to buy 12 donuts at once. Fireworks sometimes come in 144, which is a gross, because if you're shooting off a bunch of fireworks, 144 really is a reasonable number. And a mole is 6.02 times 10 to the 23rd. Again, remember, the reason the number is so big is because we're measuring something that's so small. So what do we measure in moles? Well, representative particles are the smallest unit of whatever you're measuring. This is where we use Avogadro's number. By the way, Avogadro's number is just another name for that big number, 6.02 times 10 to the 23rd. So what we do in chemistry is we've got 4 major types of chemicals. The first one, calcium, is straight off the periodic table, so you should know it is an atom, or we could say element even. So an atom or an element's representative unit is an atom. I'm going to go ahead and add element right there. Now if I put a charge on it, now it's an ion, and the representative unit of an ion is simply just an ion. Calcium oxide is an ionic compound. The representative unit of ionic compounds are formula units, back from Unit 5. And do you remember, if this is ionic, what kind of a compound water is with 2 nonmetals? It's covalent, and the representative unit, molecule. So the mole, as we talked about in the mole map, can be related to 3 other units. One is mass. The mass of 1 mole of an atom is given on the periodic table. This is known as the gram formula mass, or a lot of times I'll just abbreviate GFM. You may see other names such as molar mass or gram molecular mass, but these are basically the same thing. We will round all masses to the nearest tenth for the purposes of this class. When finding the mass of a compound, you have to add the masses of the individual atoms. Make sure that you multiply each mass according to the subscript of the type of atom it represents. So let's go through some examples. First, let's just start with an atom, calcium. You want to look on the periodic table. Remember, the mass is written underneath the symbol for the atom. So if we look under calcium, it says 40.08. What is that rounded to the 10th place? The 10th place is 1 after the decimal. 40.1. So calcium has a mass of 40.1. H2O2 is hydrogen peroxide. It has 2 hydrogens and 2 oxygens. Since hydrogen has a mass of 1.0, and there are 2 of them, I'm going to multiply 1.0 times 2 to get 2.0. Oxygen has a mass of 16.0, also multiply by 2 to get 32.0. So together, 2 and 32 make 34 grams. What about ammonium carbonate? Here's an ionic compound. So think about it. Ammonium has 1 nitrogen, 4 hydrogens, and there are 2 ammoniums. So I'm going to do 14 for nitrogen. Each hydrogen is 1 times 4 is 4. So ammonium is 14 plus 4 is 18. Because of this little subscript out here, I'm going to multiply that by 2. So that's 36. Now I'm going to add carbon's mass, which is 12. Oxygen is 16 times 3 is 48. So the ammonium is 36 plus 12 for carbon plus 48 for oxygen. So the GFM for ammonium carbonate is 96 grams. The last part of the mole map is the volume of a gas at STP. Moles cannot be directly linked to the volume of a chemical that is a solid or a liquid, only to a gas, and only when it is at STP. STP stands for standard temperature and pressure. These conditions take place at 0 Celsius, so that's our standard temperature, and 1 atmosphere is standard pressure. A mole of gas at STP occupies 22.4 liters. So that's the third part of our mole map. Now that we have all of our different types of units that we can convert with moles, we're going to use the process of dimensional analysis to solve problems. Think of dimensions as units, and analysis means to analyze or to solve. When we solve and we answer, we're going to use significant figures. The number of significant figures is the same as the number of sig figs in the known. So all the other values that we use to solve are constants, so we're not going to use any of those to help us determine sig figs. It's just the number that's in the known that will be the number of sig figs in the answer. We're going to start with some really basic examples. We're going to start with one-step problems. So we're either going from the mole or to the mole. Let's look at the first example. Determine the number of moles in 33.6 liters of helium gas. I'm going to give you a step-by-step process. I suggest you write it somewhere so that you can follow it as you do different problems. Step 1, we always start with the known. So in this case, the known is 33.6 liters. Notice I wrote the unit as well as the number. Step 2, set up a conversion factor for each move on the map. Well, thinking back to the problem, it said determine the number of moles in 33.6 liters of helium gas. So if I look at my mole map, I'm starting with the volume, the liters, and I need to solve for moles. If I think of this as a map with each of these areas as a place on the map, I'm only needing to go down one road from volume to mole. So I'm going to use what we call one conversion factor. And a conversion factor is simply a fraction that compares two values. So I've set it up with my known times my one conversion factor. Step 3, I'm going to put units along the top of the conversion factor. The top path follows the map. So remember, we're going from liter to mole. So what I mean by top path follows the map, we start with liter, and the top of the conversion factor gets the unit mole. Step 4, we're going to put units along the bottom. The bottom path follows the top. And what I mean by that is the unit comes on down. So whereas liter unit was up here, I'm going to move the liter unit down to the bottom. So top path followed my map, liter to mole, bottom followed the top, liter came on down. Step 5, I'm going to add the appropriate values into the equation. So anytime I have liter, I'm going to use the number 22.4 in a conversion factor. Anytime I have mole in a conversion factor, I'm going to use the number 1. representative particles, we would use Avogadro's number, not in this problem, but if we had it. We also don't have mass in this problem, but if we did, we'd go back and use the GFM. So in this particular problem, I'm going to put 1 in front of mole and 22.4 in front of liter. Step 6, when I solve, I will multiply anything on top and divide by anything on bottom. 33.6 divided by 22.4 is 1.50. Notice that I put a 0 there. The reason I did that was to reflect at the beginning there are 3 significant figures. So I need that 0 there to show a third significant figure. Because step 7 is to make sure to answer with proper sig figs as well as with a unit. So let's go back and look at unit. Liters are going to cancel each other out. Mole is the unit that's left, which makes sense because the beginning question said determine the number of moles. Let's move on to question 2. Again, I'm going to start with the known. How many molecules are there in 4.00 moles? So 4.0 moles. Now I'm going to observe my map. I'm at mole, and it's asking me to go to molecules. Remember, molecules is a representative particle, so I'm going up, and it's only one step, so I only need one conversion factor. So the top path follows my map, molecules goes on top, bottom path follows my top, so since mole is here, mole moves down to the bottom. I put my numbers in. Any representative particle will get Avogadro's number. Anytime I have mole, I'm going to put the number 1. Since the numbers are on top, I will multiply. And this you might not know how to do quite yet, so let's talk about how to do this. You will need a scientific calculator to perform this calculation. So I went ahead and got a calculator on Chrome. This is just a Chrome app. If you want to, you can also use an extension, whichever you like, or just use a regular calculator. So when I'm using this calculator, I'm going to go ahead and put in my equation. So I'm going to start with the 4.00, and then my times sign is this little asterisk. Okay, or I could just click on times. Then I need to multiply it by 6.02 times 10 to the 23rd power, which is Avogadro's number. Now, on your calculator, you might have this x to the y key. Sometimes it will just be this caret key, this little caret thing popped up, that little, looks like a little pointed up arrow. So sometimes the calculator will have that instead of the x to the y. Either way will do, but you want it to basically come out as 6.02 times 10 caret 23. And it shows my answer down here, 2.407, lots of 9s, times 10 to the 24th. So let's go back and think about significant figures. I'm going to need 3 sig figs because 4.00 has 3 significant figures. So rounded to 3 sig figs, it's going to be 2.41. So I've got 2.41 times 10 to the 24th molecules. Moles is going to cancel out, and molecules is what I've solved for. Now, I would suggest to you that you try to set up number 3 on your own before moving on. So we have 7.20 moles. We're going from moles to grams this time. So top path followed the map, mole to gram. The unit mole came to the bottom. The number in front of mole is 1. And then for grams, I'm going to use the GFM. So dinitrogen trioxide is N2O3. Nitrogen is 14 times 2 is 28. Oxygen is 16 times 3 is 48. And when I add those together, I get 76. So that's where this 76 came from. Now I'm going to do 7.20 times 76 with 3 significant figures. It's 547 grams. Again, number 4, I would encourage you to try on your own before checking your answer. Start with the known, 922 grams. Top path follows the map. I want to go to moles. 922 grams times 1 mole over 159.6 grams. The unit gram came to the bottom. This time I'm going to divide because the 159.6 is on bottom. So 922 divided by 159.6 with 3 significant figures is 5.78 moles. Make sure to answer with proper sig figs and a proper unit each time you do a problem like this. Now some of the problems will be 2 steps. So if we started with mole or ended with mole, it was only 1 step. But now we're starting with grams, and the problem asks us to find liters. So if we look at our mole map, we can see grams is here, liters is over here. I have to go from gram to mole, then to liter. So this time I'm going to need 2 conversion factors. So I start with my known, and I do 2 conversion factors. So remember when we do the top, step 3, top path follows the map. So again, we're going from gram, we have to go through the mole, and then down here to liters. So the way my problem is set up is the known with grams, top path mole, liter. What about the bottom? Well, remember step 4, the bottom follows the top. So whatever unit was on top before is coming to the bottom. So we have grams up here, we're going to put grams down here. We have moles here, we're going to put moles down here. Then we're going to use our numbers from our mole map to fill them in. So we're going to do step 5, add the appropriate values into the equation. So in front of grams, we need the GFM. In front of mole, we need 1. And in front of liters, we need 22.4. So the GFM for carbon monoxide, CO, is 12 plus 16 is 28. I've got moles 1 and 1 here, and then in front of liters, 22.4. So calculating, we need to do 543.3, divide by 28 since it's on bottom, multiply by 22.4 since it's on the top, and what we end up with is 434.6 liters. Check your sig figs, started with 4, end with 4, and your unit, liters. What about this next one? Again, because we're not ending or starting with moles, we need 2 steps. Start with the known, 3.00 liters, and we need 2 conversion factors. Do you know what they are, what goes on the top of each of these? Follow your map. Liter to mole to gram. Bottom follows the top, so liter comes down here, mole comes down here. Put your numbers in. 1 for mole, 22.4 for liters. The GFM is 36.5, again round to the 10th place. Hydrogen is 1 and chlorine is 35.5. When you divide on the bottom and multiply on the top, you end up with 4.89 grams with 3 significant figures. Try to set up number 7 on your own. You need 2 conversion factors again. Molecule to mole to gram. Bring molecules down, bring moles down. Put your numbers in, 1 in front of mole, 6.02 times 10 to the 23rd in front of molecule. The GFM for glucose, C6H12O6, is 180. That came from 12 times 6, 1 times 12, and 16 times 6, and then add them up for 180. When you solve, this one's a little tricky because this exponent will not be right if you put it in the wrong way. So we start off with 4.54 times 10 to the 34th. Remember, we're going to put it in 4.54 times 10. We're going to use that x to the y or caret key, whatever you have on your calculator, 34th power. Then we're going to divide. When we divide, I'm going to put this inside of some parentheses. So I'm going to do 6.02 times 10 power key 23 in parentheses. The reason I'm doing this is because I need it to be dividing the whole thing, not just the 6.02. If I don't put it in parentheses, it'll end up multiplying by the times 10 to the 23rd. And then at the end I need to multiply by 180. Okay, so here's my number. This particular online calculator did not put it into scientific notation for me. That's okay though, I can figure it out. So I need 3 significant figures because 4.54 is 3 sig figs. So I'm going to say the 1, 3, I'm going to round the 5 up to a 6. So 1.36 times 10 to the, let me move my decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1.61 times 10 to the 13th grams. Try number 8 on your own. Here's the solution. 43 liters. We go liter to mole to molecule. Liter comes down, mole comes down. I've put the appropriate numbers in. And 2 sig figs, 1.2 times 10 to the 24th molecules. Be prepared tomorrow in class to do some practice examples.